Hi everyone, in this video I'm going to do another primary amine reaction where we start with an imine, but this reaction is a little bit tricky because our imine is in a ring, and I feel like these reactions are a little bit harder because we're starting with a ring and it looks a little bit funky, so just bear with me. Since we know that we're starting with an imine, that means that we're trying to form a carbonyl at the very end. But what's different about this reaction is that our carbonyl and our nucleophile, the primary amine, are going to be on the same molecule, which is why it's a little bit funky. It's an intramolecular reaction versus the previous videos that I posted where we had an intermolecular reaction. So if you remember the last couple videos, you know that we started with an imine, and here we have an imine, and the first thing that we're trying to make is our hot electrophile. So how do we do that? Well, in order to make a hot electrophile, our nitrogen that's there is going to grab onto a hydrogen in our solution. And this hydrogen can really come from anywhere. Since we're reacting in an acidic solution, we know that water is present. So really we could be taking it from water or from the acid itself, who cares? So now our nitrogen has a hydrogen on it, still double bonded, and now it's going to be positively charged. This is our hot electrophile. And we know that since this carbon is double bonded to the nitrogen, this carbon will eventually be our carbonyl carbon. So at our hot electrophile step, this is kind of the funky part, but since this carbon is so electrophilic, our nucleophile, in this case, water, going in the backwards reaction, is going to attack our 2B carbonyl carbon, giving a lone pair back to the nitrogen after the double bond breaks. So now we have no double bond, where we have our nitrogen. This is our carbonyl carbon, but now this is the CH3 that was there before, so we're just going to leave that there. But now we have our water that just added onto it, and this hydrogen is still there. So at this step, we know that we are trying to form a carbonyl. So the first thing that we have to do is make our oxygen happy. So something in our solution, probably water, is going to grab a hydrogen off of the oxygen, and we're going to make our oxygen happy. This looks really ugly, I'm sorry. So now we have our OH, and our nitrogen's happy, our oxygen is happy, so that means that we are at our hemi-amino state. So now this is the really weird part where we're trying to find a way to break this ring. And we can't do that right now because everything on our ring is happy. The oxygen's happy, the nitrogen is happy. So we have to give a reason for the ring to break. Just like how when we did the backwards reaction before, we had to give a reason for the nitrogen to leave. We have to do the exact same thing, but in this case, we're trying to get this CN bond to break. So how do we do that? Well, we can protonate our nitrogen. So our nitrogen is going to grab something in our solution, hydrogen from water, who cares? And once it grabs that hydrogen, it'll be positively charged. So I'm going to redraw the molecule. I have our nitrogen, but now it's bonded to two hydrogens. This carbon is still there, and this OH is still there. Our nitrogen is positively charged. So now this is the part where we're going to form our double bond. We're going to form the carbonyl. And we know that because our nitrogen is unhappy, we're trying to get it to leave. So our oxygen's lone pair is going to fold over, form a double bond, which breaks this carbon-nitrogen bond. Because if a double bond is going to form here, that means that the carbon here is going to be too crowded. It's going to have a double bond, and it's going to have a bond to this carbon and a bond to this carbon. So it can't have this carbon-nitrogen bond, and it's much easier to break this carbon-nitrogen bond than it would ever be to break this carbon-carbon bond or this carbon-carbon bond. And we're really trying to treat this whole nitrogen group as, quote, a leaving group. So when this oxygen's bond folds over to form the double bond, or the lone pairs fold over, this carbon-nitrogen bond is going to break. So I like to keep my broken ring in the same kind of formation, but I'm going to number my carbons. I really feel like it's important to number your carbons. So I'm going to make this my 1 carbon, 2, 3, 4, 5. 5 is my 2B carbonyl carbon, and then this is carbon number 6 in our molecule. So now I'm going to have, I'm just going to draw the exact same thing. This is my 1 carbon, 2 carbon, 3, 4, 5. I'm going to draw carbon 6 down here, my one carbon is connected to my nitrogen. That looks really ugly. Oh well. My one carbon is connected to my nitrogen. How do I know that? Because in the previous molecule, my one carbon is connected to the nitrogen. And it's definitely okay to reason through problems like this because I feel like it's difficult to keep everything straight. So I like to think of what they're connected to, and using numbers is really helpful with that. So my nitrogen is still bonded to two hydrogens, but now that this carbon-nitrogen bond has broken, I have to worry about my carbonyl because that's what we just formed. So on my 5 carbon, now I'm going to have the carbonyl, and I know that because that's what we just did in our last step right here. The lone pair folded over to form the double bond, breaking this bond. This is the hardest part of the reaction, is breaking the ring. So that means that my 5 carbon is going to have the carbonyl carbon, but my oxygen is still bonded to a hydrogen. So that makes my oxygen positively charged. And if this part of the reaction is super tricky for you, I totally recommend going it over and over and over again because this is really the hardest part. Because now we're almost done. We had our imine, we formed our hot electrophile, we formed our hemi-amino, and now we're trying to make our carbonyl carbon happy. So to do that, we're going to have something in our solution, probably water, is going to take off this hydrogen, which makes our oxygen happy at the very end. So I'm going to draw it the exact same way. 5, put the 6 over here, and draw this down the next time. So now I'm going to make sure my carbons are all right. I have carbon 1, 2, 3, 4, 5, 6. Off of my 1 carbon, I have my NH2, NH2. And now I'm done. I formed my carbonyl after making my oxygen from the previous step happy. So I'm going to zoom out a little bit and we're going to go over it together. So I started with my imine here, and I knew that I was trying to form my hot electrophile. This is my hot electrophile. And it's a hot electrophile because this carbon is super electrophilic, and after we formed our hot electrophile, we had our nucleophile come in and stick onto our what will be our carbonyl carbon. We made our oxygen happy, and then we formed our hemi-amino. This is our happy molecule. But since we know that we wanted to break this ring and treat this nitrogen as a leaving group, we had to protonate the nitrogen to give a reason for this carbon-nitrogen bond to break. So when this nitrogen's protonated, this carbon's like, yo, what's going on? This nitrogen's like, yo, what's going on? So the oxygen's going to fold over, form a double bond, and break this carbon-nitrogen bond. And this is the part where I totally, you should number your carbons, please. Number your carbons. So I broke my ring, but I just kept it in the same kind of formation. It doesn't have to look pretty as long as you get the answer right. So I numbered my carbons all the way around. I knew that my carbonyl was going to form on carbon 5 because that's where my oxygen is off of carbon number 5, and it folded over to form a double bond, so that means that the carbonyl is going to be on carbon number 5. I also know that it's going to be on carbon number 5 because my nitrogen is bonded, or was double bonded, to this carbon. So this has to be my carbonyl carbon, has to be, especially for a primary amine reaction. Duh. So, not duh, but you know what I mean. So after we broke our ring, we had to make our oxygen happy. So something in our solution, probably water, is going to grab a hydrogen off of that oxygen and then form our final product. So now, in the next video, I'm going to do this exact same reaction, but in the forward direction. So you can kind of see how it works in both ways. So I hope this video is helpful, and let me know if you have any questions.